Hello, welcome to the part 2 of our lesson on moment distribution method of structural analysis. My name is Engineer Dr. Ididiomi Ambrose, Department of Civil Engineering of Akwa State University. Please don't forget to like and subscribe to this page so that you will be getting subsequent uh, lessons whenever I post it. So we are going to continue from where we stopped in part 1 of our lesson. So this is part 2 of our lesson, and this part what we are going to do is to look at the basic steps in finding solution to moment using the method of moment distribution. And so that is what we are going to do in this part. Now the distribution method can be illustrated with the following example. It is desired to draw the bending moment and the shear force diagram by computing the bending moment and shear force at salient points of the given beam as shown below. So this is the beam that we are given. What we need to do is to draw the bending moment diagram and the shear force diagram of this beam. So we are going to follow it step by step. So the first step is to calculate the stiffness factor, and this is similar to what we have done in the first example in our part 1 of this lesson. So if you haven't watched the first video, please try and watch part 1 so that you can follow up. So first we calculate the stiffness factor. So for member AB is fixed here and continuous here. So it's considered to be fixed at both ends. So for that case, the stiffness factor of member AB is 4 EI over L. And so 4 EI over L here, which is 8. That's 4 plus 4. So you have this of the stiffness factor for member AB. For member BC, you do the same thing. It is continuous here, continuous. So it's considered to be fixed at both ends. So it's again is 4 EI over L. If you put the L, it becomes this. For member CD, the stiffness it is continuous here and fixed here. So it's considered to be fixed at both ends. So again, the stiffness factor is 4 EI over L. If you do that, you have this. We now go to distribution factor. At AB, A going to B, as at this joint A, there is only one member meeting, so the distribution factor is 1. And at this joint CD, there is only one member meeting, so the distribution factor of D going to C is 1. That's what we said. Distribution factor of AB and distribution factor of DC is equal to 1. But at joint B, at joint C, that is where we calculate. So let's go to joint B. For joint B, we have B going to A and B going to C. So distribution factor of B going to A is what we call DFBA, and it's the stiffness of member AB all over the sum of the stiffness of member AB and BC. So this is what we do here. If you put these values here, so we have 0.33. We do the same thing for B going to C. Stiffness of member BC all over the sum of stiffness of member AB and BC. So that gives us this. Again, as a confirmation, if you had 0.67 and 0.33, it will give you 1. That tells you what you're doing is right. In the same manner, you can calculate the stiffness factor of BC going to B and C going to D. When I did that, it gives me 0.67 and 0.33, because if you notice. So the next thing we go to determine the fixed end moment. For member AB is only one load, concentrated load at mid-span. So for the left hand side, you have minus BL over 8, which gives you this. And for the right hand side, you have BL over 8, which gives you this. That's why you have fixed end moment for AB and for BC. Now for BA. Now for this band, you have fixed end moment for BC minus W. The left hand support is minus WL squared over 12. This is here. So you have this, and it gives you this. and the right hand support is will be fixed end moment of CB. So it's here. The right hand support WL squared over 12 gives you this. And for this last span, we have fixed end moment at CD, that is C going to D, this point. The fixed end moment is the minus BL over 8, and that gives you this. For DC, D going to C, fixed end moment is PL over 8, and that gives you this. So with this, we have been able to find the stiffness factor, the distribution factor, and the fixed end moment. We can now proceed further to the actual moment distribution. So this is where we do the actual moment distribution. So please pay attention. So you have here, this is the beam, and this line represents what happened at each of the joint A, joint B, joint C, joint D. So the first thing that we do is to place the distribution factor. So this first row here is for distribution factor that we have calculated. For this joint A, remember we said only one moment joining, so that's why we have for A going to B, distribution factor is 1. At the other end, distribution factor is 0 because there is no member there. The same thing happened at D. For here, distribution factor is 1. There is no member in this other side, so distribution factor is 0. So we now put the distribution factor that we calculated at each of the joints. Remember, this was 0.33, this was 0.67, this was 0.67, this one 0.33. So we have now put the distribution factor. The next thing we are going to do is to put a fixed end moment for each of those support. At this support, remember the fixed end moment was minus 40. Remember, fixed end moment is in kilonewton meter. For this point, it was plus 40, this was minus 32, this was 32, this was minus 20, this was 20. So for now, we have put the fixed end moment. The next thing we have to do is to start the distribution. Remember, we said that in this method of fixed end moment, we assume that the joint is fixed. So when you assume that the joint is fixed, that is when you have this fixed end moment. So this joint is fixed. So you have, that is where we are placing the fixed end moment. Now the next thing is for us to release the joint. When we are releasing the joint, this joint is originally fixed. This is a fixed support, so there is nothing to release. We just allowed the moment to be there. We can't release it. But this joint is continuous. It's not originally fixed. So when we release this joint, what we are going to have is that when we release the joint, we have two moments, 40 in this side, 32 in this side. And the moment, so if you do 40 minus 32, you have a moment of 8. Remember, 8 kilonewton meter. And 8 kilonewton meter is a clockwise moment. So we have an excess of clockwise moment of 8 kilonewton meter at this joint. So for us to balance it, we need to introduce an anti-clockwise moment of the same magnitude. So we are going to introduce a moment of 8 minus 8 kilonewton to balance. And how, when we introduce that moment of 8 kilonewton and place it here, well, how do we place it? We are going to place it here in the ratio of their stiffness factor. So at this point, it's going to be minus 8 multiplied by 0.33. That gives us this value. At this point, it's going to be minus 8 multiplied by 0.67. That gives us this value. So we have been able to introduce a balancing moment. And that balancing moment will distribute them based on the distribution factor to the members meeting at that joint. So if we come to this other joint, we release it. When we release, we will have 32 minus 20. That will be 12. So we have an excess moment of 12 kilonewton meter. For us to balance this joint, we need to introduce a moment which is opposite in sign direction with the same magnitude. So we are going to introduce a moment of minus 12 kilonewton meter. And that minus 12 is going to be distributed by the members meeting at this joint based on their distribution factor. So this is minus 12 times 0.67, we have this. Minus 12 times 0.33, we have this. And because this joint is fixed, we are not doing anything there. We just leave it there. So this is where we balance. Now, this is where the concept of carryover comes in. We now carry over half of this to the opposite joint. You can see this goes here. There was nothing here, so there is nothing to carry over to this point. This load, we now carry over half of it to the opposite joint. When we come here, half of this one comes to this opposite joint, and half of this one comes to this place. By that, we now have the carryover. When we have the carryover, we automatically introduces excess load again. So remember, this fixed joint, you don't do anything, just carry over things to the fixed joint, carry over to the fixed joint. You don't need to balance. But at these two joints that are not fixed originally, we need to balance them. So when we come to this point again, we now have an excess load of minus 4.02. This is a load of minus 4.02, and it is an anti-clockwise moment. For us to balance that joint, we need to introduce a clockwise moment of the same magnitude. So we have a moment of plus 4.02, which we distribute to these two members, the members meeting at that joint based on their distribution factor. So this is 4.02 multiplied by 0.33. This is 4.02 multiplied by 0.67. We come to this joint again, we have an excess load of minus 2.68. So we need to introduce a load of 2.68 and distribute to the two members meeting at that joint based on their distribution factor. So that gives us this. So once we do this balancing again, the next thing is to carry over. We carry over half of this to this, half of this to this, half of this to this, half of this to this. And once we look at here, remember you don't balance anything here because it is a fixed support. If it were to be simply supported, it would have been otherwise. You don't balance anything here. You now balance these two. When you pass through the process, you now have this. So with this, you carry over again, carry over this, carry over this, carry over this, and you now introduce another unbalanced moment, which we need to balance. When we balance that, it gives this. In moment distribution method, you keep doing until when you have the values of moment become small like this, you stop. And usually stop at the balance, don't stop at the carryover. So after stopping here, what we do, we come here, observe all the sign, add all the moments here on this column, taking note of the sign. So that gives us minus 40.8 here. At this point, don't add the distribution factor, please. You add the moments. You add moments here, give us 38.54. If you add here, it gives you minus 38.54. You do the same thing here, you have 23.42 minus 23.42. You will notice that at each of these joints that have two members meeting, you always have the moment being of the same magnitude but opposite in direction. You can see this 38.54 is minus 38.54. This 23.42 is minus 23.42. It now tells you that what you're doing here is right. The meaning is that this joint is now at equilibrium because he has a clockwise moment of 38.54 here. Here he has an anti-clockwise moment of 38.54. So that is what keeps the joint at equilibrium. So with this, we have been able to find the support moment. So this is step 3. The step 4 is drawing a bending moment diagram. Now, the principle of superposition will be used in drawing the bending moment diagram. And what does the principle say? That the bending moment diagram of a support moment is superimposed on a simply supported bending moment diagram. And the simply supported bending moment diagram is a bending moment diagram of a load based on each span being treated as simply supported. So let's go ahead. So this is the process of drawing the bending moment diagram. This is the load, the beam being loaded, span AB, BC, and CD. The first thing, this is the moment, support moment that we have calculated in each of the span, disregarding the sign. The moment is here was 40 here, this place it was 38.54, this joint was 23.42, and this joint was 18.23. We call this the support moment. So this is the bending moment diagram due to the support moment. And if you notice that support moment are usually regarded as positive, as negative, and negative bending moment is usually up. So for the next one, we have what we call simply supported moment. The simply supported moment is when you consider each of the span as if it is simply supported, and you now find their bending moment diagram. So for this example now, if we take span AB to stand alone and be simply supported, this is what the bending moment diagram will look like, where the maximum point here will be where you have the point load at mid-span, and the magnitude of will be PL over 4. These are standard formula, PL over 4, for a case where you have a point load acting at mid-span. So this is standard, give us this 80 kilonewton meter at this point. When you come here, this is span BC. If you treat it as a stand-alone span, simply supported, this is the shape of the bending moment diagram, where the maximum will be WL squared over 8. We should be familiar with this. And WL squared over 8 gives us 48. The same thing here, if you take this as a simply supported span with a load at mid-span, it will still be PL over 4, which is 40. So what we now do is that here, we carry this simply supported load and superimpose on the support moment. Sorry, we carry this simply supported moment and superimpose on the support moment. This is what we do. For instance, if for span AB, we pick this place and put it here. We pick this place and put it here. This is what we have here. How do we know what is here? How we know what is here is that if you put this here and this here, remember they are not at the same horizontal level. This one is 40.8, this one is 38.54. But at the middle, to know the value at the middle is going to be this plus this divided by 2. That will give you what is here. And you now take what is here. From that means, remember from here to here is 80. So if you know what is here is from here to the neutral line. You subtract it from the 80. That gives you this what is here. That's why we know that is what this means, is that the moment at this mid-span is 40.33. We go to span BC. What do we do? Span BC. If we take this point, join here, take this point, join here, what we will have is here. This is 38.54, 23.42. What will be at the mid-span is this plus this divided by 2. So that gives you what is here. And that what is here is actually from here to the neutral line. To know what is remaining here is going to be 48 minus what is here. That gives you this 17.02. And you do the same thing at this span BC. That gives us this. And by this we have been able to calculate the to draw the bending moment diagram for the beam. The next thing is for us to look at the shear force diagram. So to calculate the support reaction, what we usually do is to use the principle of static, and we use it and apply separately on each part of the structure. So below here is a free body diagram. This is the structure we are analyzing, and this is the free body diagram of the structure. So this span AB. Span AB, we have a point load of 40 kilonewton acting here at mid-span. Remember, we calculated the support moment here to be 40.8, and it is a clockwise moment. You can see the way the arrow comes down. At this point, we have an anti-clockwise moment and a clockwise moment. Remember, the arrows are down. So we have 38.58 kilonewton meter. This span BC, if you change this UDL to point load, this will be 24 multiplied by 4. So that gives us 96 at the place it at mid-span. And so we come here. Remember, the support moment here was in this side. It was a moment of 23.42, but this side was anti-clockwise and this side was clockwise moment. So we come to this point here. We have a point load here at mid-span, and we have a moment here of 18.82. That's where we have, this was a clockwise moment. So this is a clockwise moment, this is an anti-clockwise moment. Clockwise moment, anti-clockwise moment. So we now split. So what we do is to take this member, span AB, and calculate the support reaction separately. So we have support reaction VA and VB1. The idea is that the support reaction at B is due to what is happening in span BC plus what is happening in span AB. So we are going to have two VB, VB1 and VB2, which at the end, if we add them together, it will give us the reaction at B, which we call VB. So if we come to this span AB, we want to use the statics principles of statics, that is sum of upward moment equals to 0, sum of vertical moment equals to 0, sum of horizontal moment equals to 0, and moment at any point equals to 0. So first of all, what do we do is span AB? We take moment at point A. So if we stand here at point A and take moment, there is an anti-clockwise moment here of 40.8. So that's why we have minus 40.8. Now, this moment, because we are taking moment here, so this place will be rotating in clockwise moment. Will be rotating, and clockwise moment is positive. That's why we have positive here. And what is the moment? Moment is force times distance. What is the force? 40 kilonewton. That's what we have here. What is this perpendicular distance? 4. So that's why we have 40 times 4. When we come here, we have a clockwise moment of 38.54. So we now put here. Now the moment due to VB1, remember moment is force times distance. And if you push it here, it is producing an anti-clockwise moment. It's producing an anti-clockwise moment. So we now have VB1, which is the force, multiplied by the perpendicular distance, which is 8. That's 4 plus 4. That's why we have minus 8 VB1, and we all equate it to 0. So if we solve this, the only unknown is VB1. If we solve for VB1, it gives us that VB1 equals to 19.72. We then go to point B and take moment again. Moment at point B. We stand here to take this moment. We will still have this anti-clockwise moment of 40.8. So we have here. We will still have a clockwise moment here of 38.54. So we keep it. But this 40, if you are taking moment here, when this produces, it will be an anti-clockwise moment. And what will be the moment? The magnitude is 40 multiplied by the perpendicular distance, which is 4. So we have minus 40 times 4 plus VBA. Remember VBA here. So VBA will be producing a clockwise moment, and the moment will be force, which is VA multiplied by the perpendicular distance, which is 8. So that's why we have plus VA. 8 plus 8 VA. We equate it to 0. And so there's only one unknown, which is VA. If we calculate for VA, it gives us 20.28. So that is it for span AB. If we do the same for span AB, we do that in span AB, we have been able to calculate VA and we have been able to calculate VB1. We now go to span BC. Go to span BC. If you follow the same pattern, you will have here taking moment at point B will derive this equation. If you follow what we had did in the first one, then you equate it to 0. The only unknown here is VC1, which is this. You now calculate VC1 and it gives you 44.22. You now come and take moment again at point C. When you take that moment, this is what you will have equated to 0. The only unknown is VB2, which is here. So if we do find VB2, it gives us this. You now come to span CD. You do the same to calculate for VD and VC2. So with that, you'll be able to calculate all these reactions in each of those spans. So what we now do is that remember that at joint B, you have VB1 and VB2. At joint C, you have VC1 and VC2. So what we do is to come for reaction at B is going to be VB1 plus VB2, which gives us 71.50. And VC is going to be VC1 plus VC2 and gives us 54.87. So this is how we find the reactions at each of the support VA, VB, VC, VD. How do we draw the bending moment diagram? So this is how we draw the shear force diagram. We start with the origin 0, which is at this point. The origin 0, what force do we have? We have a force VA, which is reaction at A, and the magnitude is 20.28, so we have 20.28 here. So this force will kick the shear force by 20.28. So this is 20.28. But between here and here, there is no load, so the shear force will remain constant at that point. When it comes here, remember this reaction was acting upward, so that's why it's moving this thing up. But when it comes here, this is a downward force of 40 kilonewtons, so it's going to push it down. 40 kilonewtons means from here to here, it will take 20.28. So what is remaining from 40 will be 19.72. So it gets here. And between here and here, there is no load, so it will also move horizontal. But when it comes to this point, there is a reaction here of what reaction of what 71.52. So you push from here to here, will push 19.72, and the remaining one you will use it to push up, which will now be 51.78. And between here and here, there is load, a UDL. A UDL of what magnitude? 24 and span 4. So what you do, if you do 24 multiplied by 4, that gives you 96. So you will push it down by 96, but because it is a UDL, it's not going to push straight. It's going to push like this. You can see it's pushing slantly by a magnitude of 96. So you will take 51.78 to come to this neutral point. The remaining from that 96 is 44.32, which you will take here. And when it comes here, there is another upward support reaction of 54.87. So it will push here, it will push by 54.87. That takes us here, which is 10.65. between here and here, no load, so it will move horizontal again. When it comes here, you'll have a load of what 20 will push it down, and it can push it to 9 plus 3, 5. And then because from here, no load, so it's going to move horizontally again. When it comes to this support, there is a load, a positive load of 9.35 that will push it and that will take it to the origin. And so that is a shear force diagram, how to draw it. And what shows you that you're right is to start from origin and also in at the origin. So that shows you that what you're doing is right. So that is it for in this example. We have been able to look at how to analyze a structure, draw the bending moment diagram, draw the shear force diagram. Please don't forget to subscribe to this page and like this video so that you can be watching subsequent one. This is part 2. Watch out for part 3 where we are going to look at other conditions. Thank you.